Hey, it's my pleasure to welcome Wesley here with us. And just before I start, how many of you grad students remember Wesley from undergraduate time? Okay, so we've got a lot of fans here.
Hopefully they're fans.
Fans or architects. Okay, so that know Wesley and have been with him in classes, and so I talked to Wesley earlier. He said this is a very familiar environment. The professors, a lot of the students, so it feels like coming home for him. So Wesley, after he finished Brigham Young University as an undergrad in 2010, he went to UT Austin and has worked there. One of the unique things about Wesley, and one of the things that professors love, is when students come with their own funding. Okay, and Wesley did that. He applied for the Graduate Research Fellowship Program at NSF and was awarded that as a graduate student. And also, just recently, he's had a very selective award that was given to him from AICHE. At this upcoming AICHE conference, he's going to be one of 5 presenters that's vying for the Cass Division Presentation Award. So he has an opportunity to, and if you have an opportunity to go to his presentation at AICHE, I'd highly recommend that. Wesley's also worked at Idaho National Labs and also the National Renewable Energy Laboratory with graduate internships. Is that right? And graduate level. So with that, I'd be pleased to welcome Wesley.
Excited to be here. It's been really fun to be back at BYU. This is a great place. And, so anyway, jump into this talk. So the title of the talk here: Improved Grid Management for Predictive Residential Air Conditioning Control. So we'll just jump in there. So what we're going to do in this talk, first we're going to talk about the peak power problem. So electricity peak is a really big deal, and throughout the country, especially in Texas. We'll get some background on that. We'll talk about our proposed solution methodology here, which is using thermal energy storage coupled with dynamic optimization. I'll give you a little more background on that and how we're using it. Talk about some simulation results based on this work, and then talk about where we're going to move using this. So just kind of by way of background, in the United States, we use about 97 quads of energy. A quad is 10 to 15 BTU. And a big chunk of that goes to buildings. So 40% of all energy consumption in the United States goes to buildings. If you look at the breakout on the right-hand side of that plot, a lot of that energy is going to heating, ventilation, or air conditioning, HVAC loads. So we expend a lot of energy to make our buildings comfortable. And so if you look at all the energy uses that go just to heating, cooling, and ventilating, 15% of the total energy in the United States just goes to make our buildings comfortable. So this is a big chunk of energy in the United States. And so I'm down at Texas. Climate's a little bit different than here. So just to give you an idea, we're talking residential too. So here's a typical breakdown of energy consumption in an Austin home. So you can see it's a cooling dominated climate. When I left Austin yesterday, it was at 80 degrees. Everybody was in shorts and flip-flops. So the heating portion is relatively small. Additionally, in the urban areas in Texas, these loads right here typically met by natural gas. So the cooling is really your big driver for electricity consumption in the homes. And the other unique part about being in Texas is that Texas has its own grid. So there's 3 interconnections in the United States. There's the Eastern interconnection, the Western interconnection, and the Texas interconnection. Texas is very proud of having their own grid. But one of the advantages there is that because Texas is its own interconnection, it's all inside Texas. They're not governed by FERC. So they have no federal regulation in the electricity grid, which allows them to be a lot more progressive in implementing electricity and energy policy there. So I'll refer to them as ERCOT, so the Electricity Reliability Council of Texas. That acronym is ERCOT. So when you hear ERCOT, that means the Texas grid. So if we look at this peak energy problem in ERCOT, this is what it looks like. So energy demand fluctuates throughout the day. That's the blue line here. And so you can see that this was June last year. The grid peak was here at 65 gigawatts. You can see also in the middle of the night, the demand was here about 35 gigawatts. That means at the nighttime, if they built capacity to meet the 65 gigawatts, they have 30 gigawatts sitting around at nighttime that's turned off, not being used, or is on standby or something. So they have a lot of capacity that's sitting around unutilized. Additionally, this is a summer day. If you go to a spring day in March or April, the load may peak at 40 gigawatts, and so you have all this capacity sitting around for months at a time that's not being used. So when you're not using the capacity, you've invested a lot into this. These are capital-intensive projects. Power plants are not cheap. Put a lot of money into them. You don't want them sitting around. So that makes energy more expensive because you're not taking advantage of the plant. You're just letting it sit and not producing anything from it. And that electricity scarcity that shows up during peak times is reflected in the wholesale market price. So in Texas, there is an open electricity market. You buy and sell electricity on the market. You just like the stock market, you have a buyer and a seller. They bid, and wherever the bids match, that's what the sell price is. And so you can see for this day, prices got up for 1 hour. They were 60 cents per kilowatt hour. But most of the time, they're down here at 2 or 3 cents per kilowatt hour. So do you guys know how much you pay for power in your houses? What's 10? Okay, so 10, 11 cents is national average. Provo City Power is a little cheaper. It's about 7 cents per kilowatt hour. So in Texas, I pay during summertime, my next kilowatt hour bill is about 14 cents, so it's a lot more. In the wintertime, it's only like 9 cents, so it averages out pretty well. So this is two issues we have to deal with. One is this: we have this peak demand, and also we have fluctuating prices throughout the day. So the strategy that we want to implement to deal with this peak energy challenge is we want to use thermal energy storage, and we'll talk a little bit more about what that is in a minute. And we also want to use my short word for this is control. It's also because I work in a group where most people in the group do control, so this is the word they're familiar with. But what I mean by control, I don't mean like your PID control. I don't mean feed-forward feedback control. I mean intelligent management or intelligent operation of your resources. And specifically what I mean by that is we're using model-based dynamic optimization. And we'll talk about that a little bit more here in a minute. But first, thermal energy storage. So thermal energy storage has a lot of advantage over electricity storage or batteries primarily because of its cost. It's not as flexible because it only covers thermal loads, not electrical loads. But the basic premise is you do a lot of cooling during the day, for example, in Texas, which happens during peak times. So what happens if you could, instead of making that cooling energy during the daytime, what happens if you can make it at nighttime and store it, and then you don't have to use it during the daytime? So a chiller is essentially taking electricity and converting it to thermal energy. But that thermal energy could be stored a lot more than electrical energy can. So that's what we're looking at doing here. And in Texas, one of the ways that's done is through big chilled water tanks. So this is the thermal energy storage tank on campus at the University of Texas at Austin. It's a 4 million gallon tank of cold water. So they make cold water at nighttime, fill this tank with cold water, and during the daytime they turn off their chillers and use this tank to supply campus cooling needs. So this is one at a hospital up there a couple miles from campus, and so work with them as well and operating their system. So the basic idea of how this works is you have your thermal energy storage and chiller plant here. They consume electricity from the grid and supply cold water to buildings. So in our case, we'll say the University of Texas campus. And they also consume electricity from the grid. They take this cold water, send warm water back, and then these two pieces work together to meet thermal loads in the campus. At UT Austin, we also have a unique situation there. We produce our own power, so we have gas and steam turbines that make electricity. It's also, we don't just worry about the electricity coming out of here. We also have a lot of exhaust heat, waste heat coming out of here. You can recover that and use that for the buildings. And then additionally, when it gets really hot outside, natural gas turbines lose capacity because the density of air is reduced. Your mass flow rate through the turbine goes down, and therefore your capacity goes down. So one way you can mitigate that is by cooling the inlet air. So you draw some of this cold water out, fill the inlet air to around 40 degrees Fahrenheit, and send it through the turbine. You get big boosts in capacity. So once you start looking at all these pieces and how they work together, it's not obvious what the best way would be to operate this system. And so that's where the dynamic optimization comes into play. Is it allows us, we model the system and then use those models in a dynamic optimization framework to say, well, what's the best way to operate this system? So just to kind of summarize how the difference between the two, if you just deploy thermal energy storage and you use some heuristics, well, we know it's hot in the afternoon, that's when we want to use it, you get a lot of peak reduction savings. So in this case, we could reduce the peak by 42% just by installing the thermal energy storage. But if you install thermal energy storage plus dynamic optimization, you improve those benefits drastically just by operating the system in the most efficient way. So there we could improve our benefits from 42% to 63%. So just by the intelligent management of the system. So in the title of the talk, I said we're going to talk about residential homes. This is just kind of give you background on the thermal storage area. So if we go back to this peak energy problem, this is why we're looking at thermal energy, or this is why we're looking at residential sector. So we have 2 days here shown on this plot. Here's the peak demand for the day plotted on this axis. And then we have 3 sectors, the industrial, commercial, and residential sectors here. So the moderate day, this is a day in March. The peak day, this is a day in August for the same year. The industrial sector in Texas, in the ERCOT grid, between the moderate day and the peak day consumes about the same amount of electricity. That makes sense because industrial loads are not really dependent on weather. Commercial buildings doubled their load between the moderate March day and the peak day in August, and that's primarily due to cooling. And then in the residential sector, you can see that the load here increased by 6-fold. And that's primarily because of air conditioning and because when it's 110 degrees outside, people want to be inside, and so they're inside consuming more energy by doing things in their home. So this really demonstrates that residential homes are really what's driving this peak demand issue. And so this is where my most recent work is focused, is on trying to deal with this problem from the residential sector standpoint. So thermal energy storage in a home is a little bit different. So we don't want to go put a chilled water tank on every house. That would be expensive and not very effective. So what we're going to do instead is store thermal energy in the house itself. So for example, in this room, there's a lot of walls, floor, chairs. If we cooled down this room, we would essentially have stored thermal energy in the room that we could take advantage of later. So the main advantage here is that the storage is free. It's already there. We're just using the house to store energy. But it does require some intelligent operation. We'll touch more on that here in a minute. It's got some challenges though. So our home is not a 4 million gallon chilled water tank. So it's got a very small capacity. And secondly, there's more integration. So if we look back at, well, okay, sorry, just skipping ahead here. So if we look at our heat equation here, this mass times heat capacity times delta T gives us the amount of energy we could store in the home. So this MCP, that's the thermal mass of the home. That's all the walls, the floor, the chairs, table, everything else in the home that can store thermal energy. This delta T represents the temperature difference between the maximum temperature you want in your home versus what your home temperature actually is. So if you like your home at 76 degrees, but your home is actually at 72 degrees, then you have 4 degrees of delta T where you can warm up your home back up to the 76 degrees. So your delta T is 4. And that also lends itself to this small capacity piece. 4 degrees is not a very large delta T for storing sensible heat. So integration comes into play because in our previous example we looked at here, we have the storage and chiller plant that are just supplying cold water to these buildings for air conditioning. They don't affect what's actually going on in those buildings. What people do in those buildings is independent of the chiller plant and the thermal energy storage. But if we look back at our home, these are temperatures inside the house. So if we're changing temperatures inside the house, we're affecting people. This is their living environment. And so it's very integrated. We can't just lower the house to 60 degrees so that we have a really big delta T and therefore more capacity for storing thermal energy. That's not, I don't want to be in a house at 60 degrees. Okay. So that's one of the challenges there. So to start moving forward with this work, first we needed to do some modeling. So we're going to use dynamic-based or dynamic optimization based on models. And so we need some models of these residential homes. So essentially what we want to do is we want to take a single home and represent it as an equation or system of equations where we can say, here's the set point in your home, here is the weather or weather predictions for the next, say, 12 or 24 hours. Then based on those things, what is the electricity consumption of this home? And we have a couple options for that. So there are building energy modeling software out there. So Energy Plus is an example of that. It's very detailed. It has lots of information about the building, very accurate. But we also have this reduced we also could look at reduced order models. So the main reason we differentiate between these two is because Energy Plus, although it's very detailed and it's our package system out there, you can just plug and play with it. It has thousands of equations. And if you're solving an optimization problem, you don't want to have thousands of equations. So we're looking, instead of using a reduced order model, to represent this home. And that reduced order model is just a single equation and makes our optimization approach much easier. So the kind of things that we're going to be looking at in this research work are we're going to try and answer these kind of questions. So I put up market prices earlier where the prices went up to 60 cents per kilowatt hour. One of the questions I always get when I started doing this work is, well, what happens if everybody starts responding to market prices? Are we just going to shift things earlier? Are we going to just shift our peak earlier in the day? Because now instead of using it at 4 o'clock, we're just going to use it at 2 o'clock before that price is set in. So we want to look at, well, what does happen if everybody starts responding to market prices? And then we also want to look at, well, how much potential is there in the residential sector, just looking at your air conditioning? How much can you actually flatten the peak? How much can you lower that? And then we also want to look at what's the value of information sharing in a community. So if you solve an optimization problem where nobody in the community knows what anybody else is doing, the results are going to be far different than if you solve a problem where everybody in the community knows what everybody else is doing. And we'll talk more about that. Just the keywords for that right now are centralized and decentralized. We'll define those here in just a minute. So to do this work, we have quite a few resources available to us down at UT Austin. So the first is Pecan Streets. They are a smart grid demonstration project funded by the Department of Energy. They have gone into this new community, new green-built community, and they've installed smart meters on hundreds of homes in the community. These smart meters have individual circuits monitored in the home. So we know how much electricity is going to air conditioning, we know how much is going to the fridge, how much is going to lighting, etc. So very granular data. This data is also collected at 1 second intervals. So we have tons and tons of data, sometimes more than we'd like. We also have a lot of homeowner surveys from these people. So they have all these participants, they send out surveys, we get results from them, so we're able to incorporate that information. We also have building energy software. I talked about Energy Plus earlier. This is developed out of NREL. I spent a summer up at NREL and it gave me some familiarity with this software. And then additionally, we've worked a lot with our local utility, Austin Energy. They provided us billing data and energy audits to the home. So in Austin, it's kind of a unique scenario. If you buy a home in Austin, or I guess if you're selling a home in Austin, you're required to get an energy audit for the home. So that's mandated by the city council. So there's a lot of information about how energy efficient the homes are. So the process we've taken to look at a community of homes, model a community of homes, and look at what kind of peaks demand reduction we could get there are shown here. So first, we're taking these energy audits. We take Google Map images of actual physical homes and the billing data from those homes, and we combine all those to create these detailed Energy Plus models. So we have 60 physical homes where we have these very detailed, with thousands of equations, Energy Plus models. And we've validated those homes using the billing data. So we could say, here's our models, and we think they're good because they match the billing data that the utility has provided to us. So we talked about how Energy Plus has thousands of equations. So that's kind of a problem if we want to do some optimization. So instead, we developed reduced order models where we could represent a single home with one equation. And apologize for not going into details about developing the reduced order model. That would take another talk, so we'll save that for later. Then from there, we could create the community. We need a larger community of homes. We only have 60 physical homes, so we're scaling up to 900. But we have a challenge of we only have 60 physical homes, and we want a 900 home community, so we replicate each home 15 times. We don't want 15 identical homes. So to diversify the homes, we take this survey information and make each home unique. So here's an example of some survey information. We sample 162 people in this smart grid demonstration area and say, hey, where do you put your set point in the summertime? And so here's the distribution of where people like to put their set point in the summertime. You see 78 is the place to be. So we could draw on this distribution directly to assign every home its unique thermostat set point. Say this number of homes wants this set point. And so that's one of the ways we make every home unique. The other way we make the home unique is we have all these profiles of how people use energy over the day. And using these profiles, we can determine when people arrive and when people leave. And so we use clustering of those electricity profiles to determine how many people are home. It turns out about half the people in Austin, based on our home, somebody's home in the house during the whole day. 50% of the home, somebody's gone during the house for part of the day. And so we get arrival and departure times from this clustering and assign those to these 900 homes. So the homes are unique in their desired thermostat set point, their occupancy parameters when they arrive from home or if they're home all day. So once we have this 900 home community, then we apply our community-wide control strategies, or how are we going to manage all these homes. And because we're looking at more than just electricity, we want to manage the whole peak, not just the electricity. That we don't care just about the air conditioning, the electricity for air conditioning. We care about all the electricity. We've been able to draw meter data from non-AC loads and implement them into this model as well. So this gives us our opportunity now to apply our dynamic optimization. So we're going to look at 3 different ways we're going to implement this. The first, we just want to minimize costs using market prices. So here we have our electricity usage times our energy costs. We just want to minimize that, make that as low as possible. The second case we're going to look at is the centralized control cases where with perfect information sharing. We'll explain that in the next slide here. This is where we want to minimize the maximum electricity usage across the whole community. So we say, what's the maximum electricity in the community? We want to minimize that peak. So how can we minimize that? And then this last one is for every home. This symbol is for all. So for all homes, we want to minimize your peak. So in this one, we're minimizing the peak. We're minimizing the maximum electricity consumption of every home, of each home individually. So this one we're looking at community. This one we're looking individually. And these optimization problems have just over 10,000 decision variables with over 20,000 constraints. But because we've implemented this reduced order model, it can solve in about 2 seconds because of the form of our model. So to clarify the decentralized versus centralized approach, this is shown here. So we have a centralized approach where we have perfect information. Some model-based dynamic optimization algorithm knows what all the houses are doing, takes in weather inputs, and assigns set points to each house. So it knows what all the set points is for every house for every hour of the day. So this is likely to give more superior results because it knows what everything's doing. In the decentralized case, we have each house with its own dynamic optimization algorithm, takes in weather input, and makes decisions for that house only rather than for the whole community. So we'll compare these cases as we move forward. So just to give you an idea about how this works, let's look at a single home. So this is, in this case, we'll be looking at the minimizing costs. We'll be using those market prices. The house is unoccupied in this case from 8 a.m. to 5 p.m. Desired thermostat set points at 78 degrees, and this is a green built home. So that means it's got good insulation levels, it's got high efficiency air conditioner, etc. So here's a SketchUp rendering of that home. And so if we apply our dynamic optimization to this to say, well, what does the dynamic optimization algorithm decide? How does it manage this home? We get something that looks like this. So the inputs are shown here at the bottom. This is the temperature throughout the day. So this is a relatively hot day. Here are the electricity prices. These are actual prices from the market. You can see that on the top, this is these dashed lines right here. This is the upper bound of the thermostat. Here's the lower bound of the thermostat. So you can see the region is narrower when somebody's home. It's wider when they're gone. We expand the range where we can put the thermostat set point. So the controller or the optimization algorithm decides to reduce, not reduce, but lower the temperature here in the morning and lower it even further when the person leaves the home to store thermal energy. So essentially we have stored thermal energy, then here in the afternoon when we raise the temperature, we're releasing that stored thermal energy to lower our electricity usage. So if we look at the electricity usage throughout the day, during this time where we raise the thermostat, that's when our electricity usage goes to 0. I've also plotted this graph, the Energy Plus model, so that very detailed model versus our linear model. You can see they match up quite well, so we're happy with the performance for our linear model we've created. So if we look at this home, we've reduced the cost by 69%, and we've reduced peak by 29%. So for one home, one day, that's how things work. So now if we look at the whole community, so now we're looking at all 900 homes. We're looking at here the base case, where the base case would be we keep our thermostat at the upper bound of its set point limit for the whole day. The energy profile looks like this. So we're peaking here in the afternoon. So if we implement the minimum cost case, we say we want to minimize our cost for the whole day, then our energy profile looks something like this. So you can see that right before this high price time, electricity usage drops. We've stored thermal energy here by cooling the homes more in the morning, and then in the afternoon we raise the thermostat set points to lower our costs. And so this results in 11% cost savings. Peak is reduced by 4%, so it is shifted to earlier. So now our peak occurs here instead of here. So we are shifting peak, but it is still lower than the previous peak. So some of the interesting things that come out of this is in that previous home you saw there was a 69% savings, and this the total savings is 11%. So if we look at why that's so different, we can see that here in the difference between a home that's occupied versus not occupied. So in the occupied home, the difference between the upper and lower bound set points are very small. You can't move the thermostat set point around very much because somebody's there. They don't want you lowering the house, making it really cold in the house. So here the bounds are small. Here, when somebody's gone from the house, the bounds get quite large. And you can see the difference is the amount of thermal energy that can be stored in the home. So here, when the thermostat set point is raised and we can use that stored thermal energy, the electricity consumption drops just a little bit. Down here on the bottom, when this thermostat set point is raised, the electricity consumption drops a lot. So we have a lot more storage in a home where somebody isn't here than in a home where somebody is here all day long. So that's a major differentiator between individual home performances. So if you look across all 900 homes and how much savings could be achieved in those homes, most of the homes that achieve high cost savings are in homes where somebody's gone for part of the day. In places where somebody's there all day, the savings are much less. It just creates challenges if you want to try and implement this program on a wide scale. How do you create this program so you're not favoring one demographic over another? So there's a lot of things that could come out of this and moving forward as far as a utility designing its rate structures or designing its policies for implementing rebate programs to try and lower peak through this method. Now, if we don't consider costs and we only consider minimizing the peak, then the results are different. So first we'll look at the centralized control case. So the centralized controller has perfect information, knows what everybody's doing. So the peak is perfectly flat here, and your peak is reduced by 10%. If you look at the case where each house is trying to minimize its own peak, then you're obviously not going to get that perfect flattening. It looks something like this. So it's close to 6% in the peak reduction. So that shows that the value of information sharing in terms of peak reduction is about 4%. So you get about 4% achievement, which doesn't sound like much. When you start talking in grid level, 4% is a lot. So that's the gap where things can be worked on, where there's still improvements to be made. So if we look at this system and we say, well, this is nice, but we also have, because it's a smart grid demonstration project here in Austin, these homes, a lot of them are outfitted with PV. So we want to look at, well, what happens now if PV gets entered into this generation mix? What's going to happen? So we're able to use the data again from the smart grid demonstration project there in Austin. So there are 226 homes there that have PV arrays. So we just took that data directly from those homes. They're 3.42 kilowatt arrays, and it's a mix of south versus west facing arrays. So just interested from you guys, why would you care if your array is facing south versus if it's facing west, your PV array?
Peak times of energy at different times. So if it's facing south, you're going to get a better average over the day. If it's facing west, you're going to get a high peak energy.
Wow, that's perfect. So during the day, so your south-facing PV is going to get more energy because the sun passes through the south, so you'll collect more energy in a south-facing array, but your west-facing energy is going to align better with peak. So west-facing PV will produce less energy, but aligns better with peak. So we have a mix of both of those, and we've taken that into account here. So that's very nice. That was great. I didn't even tell him to do that. So anyway, if we go back to our community and we look at what we had before, shown here in the light blue, and then we say, well, now we're going to put in PV, then now our generation looks like this. So all this area in here, this is all generation by photovoltaics. So you can see a couple things happen here. One is our peak is lowered by quite a bit, and also it's shifted a lot later just by implementing PV. Now, if we implement again this decentralized strategy, we get something that looks like this. We are able to lower peak a little bit, and then if we look at the centralized strategy, it looks almost on top of it. And so what's happened here? The reason we don't have a discrepancy between the centralized versus decentralized methods is now all the homes are peaking at essentially the same time. Every home peaks right around here. And so if we are trying to minimize the peak of all the homes, it's identical to minimizing the peak of individual homes. So there, the value of information sharing is essentially zero. Minimizing the peak of individual homes gives you the same benefit of looking at all the homes. So, so that's kind of interesting to see. The other thing that's interesting here is that before we're going from a load of about 1,000 up to about 5,000 in a few hours. Now we're starting even lower and ramping up to almost to the same spot, but in a shorter time horizon. So if you think about an electric grid, most of the capacity on a grid is thermal generation, and thermal generation is typically not really fast. So natural gas turbines are fast, coal power plants are not fast. Something that's got steam cycles in it, those are slower. So one of the concerns with PV that's demonstrated here is that as you ramp this up really fast, it's going to be really hard for the grid to respond to that. It may mean you have to have more standby capacity, which means you're burning more fuel to just stand by and be ready to respond. So that's one of the challenges, and one of the areas we'd like to look at in the future is, well, instead of just trying to minimize peak here, which isn't as effective once there's PV in place, could we manage our air conditioning load to make this not ramp so quickly? Could we fix that ramp rate by moving around our thermostat set points in our house? So let's see, I want to show one other thing here. So one other thing that we've done for information sharing is we've developed, I'd like to show it a new scenario here. So we saw that the value of, without the PV, the value of centralized control was a 10% peak reduction, of decentralized control was about 6%. So we had that gap of 4%. So this is one of the methods we've used to try and not have to do information sharing, but still get that 10% peak reduction. So instead of implementing a minimizer peak, we're going to try and use a more economic objective function type approach. So here we're going to give every home a penalty term that looks like this. So we have, for 21 hours of the day, the penalty for using electricity is very low. For 3 hours of the day, the penalty for using electricity is very high. So this would be analogous to some custom pricing scenario. So we're going to assign, we don't want every home to have this exact same profile because then they would all respond at the same time whenever that peak hit. So we're going to start the homes at different times with this profile. So the profile we developed that we found to be effective is shown here at the bottom. So for example, 20% of the homes are going to have this 3-hour high price period starting at 3 o'clock p.m. And so every home just randomly has this profile assigned to it starting at a time drawn from this distribution on the bottom. So then when we look at implementing centralized and decentralized control, we find that they're basically the same. So if we give these custom prices, or these custom penalty terms to people, we don't have to do any information sharing. If we just distribute when we start the high price periods or when we start giving people incentive to reduce consumption, we could essentially achieve the perfect information sharing result without sharing information. And so that's really advantageous. Information sharing is not something people are typically very favorable of. And it's interesting too, been some discussions and you start talking to people and you find out there's a lawyer there who wants to know if he could subpoena your electricity use information for help in a divorce case to find out when people were home. And so anyway, it gets really messy and utilities don't want to have that responsibility on them. So, so that's one of the things we're trying to do here is just alleviate the need to have information sharing. So you can implement these peak reduction strategies without that. So let me take you to here. So just want to finish up here by just kind of talking about some path forward here. So so we've been able to use in the residential area, which is not your traditional, we're going to go look for energy savings by managing residential homes better, by applying dynamic optimization, taking advantage of thermal storage. It's not a typical area to go look for energy improvements. But the strategy is shown to be potentially effective. So I'd like to look for ways to apply this strategy to industrial facilities, finding storage opportunities there where we can implement these kind of opportunities. And then we get more scale involved with that. We also want to couple this strategy with industrial facilities. So if you have, for example, a industrial facility co-located with a residential or commercial community, they have different loads, but they're in the same grid. Could they work together in some way so you could actually manage the loads in an industrial community with the air conditioning of a residential community, provide optimal grid benefits? So is there a way that by looking at both of them, you could adjust one to compensate for the other, or vice versa? There's also opportunities in that for looking at ways to share resources, such as waste heat, or water management. So for example, if we use treated water for irrigation or for other uses such as that. And then we talked about this PV ramping problem. So when PV dies off, you have a very steep ramp in electricity. So designing strategies to deal with that. And then lastly, how would implementation work? So this is nice in simulation, but you can't simulate people, and simulation is not real life. So even though it'd be nice to think that sometimes. So how would you actually implement the system? Would you have an aggregator? Would you have a utility doing this? How would you manage? What kind of incentives do you need to give people to get them to participate? What kind of participation levels do you expect? So that's kind of path forward there. And then lastly, just would like to acknowledge some people who have been helpful with this. My mentor at Enron, Whitehale, who's a graduate from UT Austin Chemical Engineering, has been very helpful. Rigor Insights, Steve Holder, has been helpful with the building related stuff. And then Tom Edgar and Mike Weber research groups. And then funding and resources have come from a variety of places here. And it's been good to work with them. So just thank you for your time. It's been great being here and happy to take it.
Okay, we've got about 5 minutes for questions, so feel free to ask. James.
So in your main goal is to minimize cost. You're minimizing that peak time to minimize cost. But that made it, you're using more energy in all cases, right?
Yes, so generally, if you're trying to minimize costs, you're using more energy. You can minimize, if you're focusing on minimizing energy, your profiles look different. But yes, in this case, we are consuming more energy to reduce the peak. That's true.
Did you quantify how much energy how much more energy you were consuming?
So it depends on the day. It's about 5 to 10%. So it's pretty close to whatever. If you get a 10% reduction in peak, it's about 10% increase in energy consumption. So it's a pretty one-to-one trade-off in terms of energy versus capacity.
Can I have a follow-up question?
Yeah.
So, but the goal in it isn't just to reduce the cost for the consumer. You talked about ramping up at a power plant. What are the cost savings of that?
So that's interesting. So right now, I don't know. We started this and we're like, hey, this is really steep. That's not good. And so it started with being ignorant to that, and now we see, oh wait, that might be a problem, so now it's got to expand and say, okay, that needs to be factored in. So that's, I don't know right now, that's a piece of future work. Yeah.
So, in the beginning, you said this is a model-based predictive control type of problem. Where's the control part? Is it just the way
So
you
it's
set up the
a
problem, or-
well, it's an optimization framework more than a control problem. So what we're doing is we're deciding what temperature set point should be in the houses for every day. So those are our decision variables in our optimization problem, is the temperature set point for each of the homes.
Have you done any optimization for motor objective, both reducing the cost and also reducing the peak?
Yeah, so I've done some, and it's very, I mean, it really depends. It's so user driven, like how much do you value reducing the peak versus the cost. It's really hard to gauge what the value is. So yes, I have done some. I don't know how to best interpret the results other than as I shift it, I can see it move one way or the other. I mean, it's kind of this nice continuum, but it's hard to say it's hard to identify the optimum using the multi-objective optimization because it's hard to decide which one should receive a higher weighting value or if they should be equal or how that works. So it's difficult to interpret results, but they are nice to see the change from one to the other. Yeah.
You made the assumption that it was a very green home that you were using. Or were you using data from the 900s?
So yeah, so that one home I showed was a green home. The rest of the homes are a wide range, so anywhere from the earliest home I think was built in the 1930s to ones built up into the mid-2000s. So there's a wide range of homes with a wide range of efficiencies. If you look at just green-built homes, the peak reduction would be a lot smaller because they're tighter, more efficient. Or be a lot greater, I mean.
Would you have a bigger impact if you made homes more energy efficient? Would you see a bigger impact by making homes energy efficient relative to a really poor home, making it energy efficient as opposed to working with thermostats?
Yes. So there's much more impact in making a home energy efficient than there is in modifying where you're putting a thermostat. The difference though is it takes a lot of money to make a home more energy efficient. It doesn't take very much money to change a thermostat set point. So it's really the capital investment, but there's a lot more potential in making, as far as total energy consumption, there's a lot more in the retrofitting of the homes than in the operation. Yes.
Like feedback on buy-in to a community to do this kind of thing. I mean, you've got all this modeling and so forth, but you got people to buy into want to do it. Are there any studies that are finding out those answers?
Yeah, so in this Pecan Street Smart Grid Demonstration Project, we have several pricing trials going on where we're exposing people to prices. As some get a text message that says, hey, today is a peak day, can you curtail? Others get pseudo prices where they get a pretend bill. So there's some of that's going on. I'm not directly involved with it, but yeah, that's happening as part of this smart
Are the people buying into it? Are they participating?
Yes and no. So like the text messages isn't working very well, but giving people price incentives, that tends to be working. So people respond a lot better to prices than just somebody asking them to do something. So.
I'm just curious how these simulations you run, are they deterministic? Is it something that you can run several times and get kind of a variance on how much these changes are? I don't know much about optimization, so I'm just curious.
Yeah, so these ones, the results I showed were all deterministic, and all deterministic framework. You could make them stochastic, and because we're using the reduced order model, that wouldn't be too difficult to do. I don't imagine the results would be too different because once you aggregate enough homes together, there's enough that are over and enough that are under that it kind of averages out. And so I don't think there'd be that big of a spread in terms of net results.
Okay, great. Let's thank Wesley one more time. If you have any more questions, you can come up afterwards and talk with us.
Just like everything.